So why do we call Euler path? So this is linked to the mathematician Euler. We have not talked about Euler before, but we will talk about this as the first result from Euler, and then the next one, when we talk about something called planar graph, it is also related to Euler. So Euler is a Swiss mathematician. So he's from Switzerland. Okay, and then but he worked in Russia. Okay, so have you heard? Okay, if you heard of Euler, if you have heard of Euler before, could you please raise your hand? Okay, if you've never heard of Euler before, could you please raise your hand? Okay, if you have never heard of Euler, how about Bernoulli? If you have heard of Bernoulli before, could you please raise your hand? Okay, so Bernoulli, if you have studied, I don't know how to translate it in Chinese, but if you have studied physics, okay, then you will have come up with Bernoulli a couple of times. Bernoulli is a name that when you study, what do we call it? Fluid, right? Fluid or pressure or whatever, fluid, okay? Actually, Bernoulli has a big family. All of them are mathematicians. So you have Jacob Bernoulli, you have John Bernoulli, and John Bernoulli has a son called Daniel Bernoulli, and they have cousins and whatever, so a big family. So Euler is actually a student of Bernoulli, and he so far, if you have not heard of him, then it's great, because yeah, today you heard of him. So Euler is considered one of the, or not one of, the most productive academic writer in the whole world up to now. Okay, so over his life, so if you count the number of publications that he has made over his life, and counting by the thickness, okay, the number of pages, okay, then he's the number one up to now. Okay, so there is another one that has died around 10 years ago called Erdős, and then Erdős is also very productive, prolific, and if you count the number of publications by this number, so I have 1 paper or 2 papers or 3 papers, then Erdős is number 1. Okay, but if you count the thickness, okay, of the total publication, then Euler is number 1. Okay, and then so we'll talk. So I would prepare some more things about Euler and talk to you next time maybe. But then, so Euler, so Euler is actually a student of Bernoulli, and actually a friend of Bernoulli's son, Daniel Bernoulli. So Daniel Bernoulli has a job in Russia, and then when Daniel Bernoulli has decided to leave his job, he recommended Euler to take up his position. So now Euler works in Russia. Okay, but on the vacation, so there is still vacation, Euler visits a town called Königsberg. At that time, it's located in Prussia. So Prussia, so in Chinese we call it 普鲁士. So it should be a place around the area of Germany. So when he visited this Königsberg for vacation, then he find that the citizens in this Königsberg on Sunday, every people walked around the town in a very strange way. So he is very curious why people go out and walk around the city, because the city has a very interesting shape. It looks like this. So there is a river. So it looks like this, that divides the city into a couple of parts. So the river looks like this. Do I have another color? So this is how the river looks like. Let me draw the river here. So actually the city of Königsberg is divided into parts that looks like this. Okay, so these are the lands. And this is the river. Is that okay? Do you understand my picture? Yeah, it's not that good. Okay, so you can see that there is an island here in the middle of this river. Okay, so there are two rivers. And then, so between them, there are bridges. So there are 7 bridges. There is one bridge here, there is another bridge here, and 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 then there is another bridge here, and there is another bridge here. Is that okay? So if you understand the diagram, then I don't need to have this one. So you have an island here, an island here, an island here, an island here. Is that okay? So they are altogether 7 bridges. And what are the citizens doing? So they are trying to find a way to cross this 7 bridges exactly once. Is there a way that you start at a certain location? Maybe I started here. Okay? So let's say I started here, and then I take this bridge to this one, take this bridge to this one, and then come here and take this bridge to here, and come back here, take this bridge, and come back here to take this bridge, and come back to take this bridge. So that after walking, we can visit these 7 bridges exactly once. Is that okay? No, we cannot. Okay, so they tried very, very hard. Nobody can succeed in doing so. And actually, it is proven by Euler that it is impossible. And that's why we have this Euler path problem. So how do we make this into a graph problem at the beginning? So you can think about that. This is land A, this is land B, this is land C, and this is land D. Is that okay? So you can think about there are altogether 4 pieces of land. So there is a land A, there is a land B, there is a land C, and there is a land D. Is that okay? Okay. So if you are at A, you can go whatever way and then go to whatever bridge that you want. So in this way, you can think of A and B are connected by 2 edges, 2 bridges. A and D is connected by 1 bridge, B and D is connected by 1 bridge, D and C connected by 1 bridge, and B and C are connected by 2 bridges. Is that okay? And now, if you look at this, this is going to be a graph that has 4 vertices, 1, 2, 3, 4, with 7 edges. And then we are asking, is there an Euler path? Is there an Euler path for this graph? Can we start at any vertex and then visit all the edges exactly once? So if we can do so, then the 7 bridges problem can be solved. If we cannot do so, then there is no way that we can solve 7 bridges problem. Is that okay? Okay? And then Euler proved that this is impossible. And this is perhaps the first result in graph theory. So wherever we talk about these are graphs, and then this is the theory about the graph theory. So how? Okay, how can we prove? So Euler has a very simple observation. It turns out at that time it is not that simple. Okay, his original paper is very, very difficult to read. But nowadays we can make it very simple. We can describe this easily. A graph has an Euler circuit. Let's make Euler circuit first. So for a graph to have an Euler circuit, we have an if and only if condition. So a graph G has an Euler circuit if and only if so we need 2 things. The first one is trivial, that G is connected. Well, so we assume that, okay, so, what I mean is the edges has to be connected. So the vertex may not be connected, but the edges has to be connected. If you have a graph G that looks like this, there can't be an Euler circuit. Yeah, because there's no way to reach from this side to this side. There's no way to reach from this side to this side. Okay, so for the first thing to happen, G has to be connected. And the second one is, so suppose that G is now connected. So let's look like this. And then the second thing is the degree of each vertex is even. Okay? So this is very, very simple. You can look at the graph and check whether the degree of all the vertices are even. If it is the case, then you have an Euler circuit. If it is not the case, then you don't. So, example. So circuit. So let's have an example. So let's have this one. Yes? Does it has an Euler circuit? Look at it. This has degree 2. This has degree 3. Okay, no, it can't. It can't. Okay, let's make it this one. Can this has Euler circuit? Well, no, this has degree 1. You don't. Okay, so let's make it here. This has degree 2, degree 4, degree 2, degree 4, degree 2, degree 4. Okay, is that okay? Let me see. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Every vertex in this case has degree even. Then we are saying that it has an Euler circuit. So let's try to get an Euler circuit. If there is an Euler circuit, actually, it means what? It means that there is a way that we can get all the vertices, all the edges, and going back to one place. So if there is an Euler circuit, it doesn't matter where we start. We can start at any location. Let's start at this point, okay? So we go to this edge, and then go, let's say we go to this edge, we go to this edge, we go to this edge, we come back, we go to this edge, 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 we come back. Is that okay? Okay, there's an Euler circuit. Okay. And the proof turns out to be easy. If we, at that time, there's nobody defines what is meant by degree. So in that case, Euler has a hard time to prove that this is true. But now we have the concept of degree, then it is easy to describe when it has an Euler circuit. How do we prove? Okay, so to prove this is true, we need to prove if and only if. Is that okay? So let's prove one side first. Okay, if a graph is having an Euler circuit, it implies that every vertex has degree even. So this is what I want to show. So I want to show that this direction first. So Euler, so let's show Euler implies all even. So if it has Euler, then it implies all of them are even. Okay, so how do we show? It's easy. Okay, look at it. So if there is an Euler circuit, then that means that we can have a path that goes all the way and back to itself. Is that okay? Visiting every edge exactly once. So when you visit an edge, okay, you have direction. So you're walking, right? So just like I'm adding arrows in and adding arrows out. Is that okay? Now if you, for each vertex that is not the starting vertex, let's say this is not the starting vertex, you have to have the same number of ins and same number of outs. Because you have more in than out, then you stop there in the end. So it is not a circuit. The only way that you can stop must be the starting vertex. Is that okay? Is that okay? So if you have this one, if you look at this vertex, let's check this vertex. It has in 1, and then in 2, and then out 1, and then out 2. Is that okay? So every time you enter a vertex, you need to leave. Every time you enter a vertex, you need to pick a new edge to leave. Is that okay? So the number of edges joining to the vertex must be even because you must have the same number of ins and the same number of outs. Is that okay? Is that okay? And how about the beginning vertex? The beginning vertex is apart from the first time you are leaving and the last time you are entering this vertex. Every time you visit this vertex, you must have in and out, in and out, in and out. So it means that every vertex has to have even degree if there is an Euler path or Euler circuit. Is that okay? Is that okay? Okay, good. Now, let's try to prove even. If everything has even and connected, then you must have Euler. Okay. Now, how do we prove? We prove this by induction. Induction. Okay. So how do we prove? So first of all, induction. Induction. Everyone has even, and then what? And then, so the simplest case is you may have one or two edges. So one edge is like you have the same joining to itself. Okay. So one, well, let's forget about this one. Let's assume that we don't have self loops. Okay. So in the basic case, we are doing induction on the number of edges of the graph. Okay. Now suppose the graph has one edge. Then one edge and two vertices, you will have odd degree. So it is impossible. Is that okay? So you can't have just one edge. So the smallest graph that you can have maybe is, let me see if it is induction. Yes, two edges. So the smallest graph that you can have is having two edges, and then each of them is even degree. Is that okay? And in this case, this is the basis case for us, and then we can find there is an Euler circuit. Is that okay? And how do we prove the general case? Okay, the general case is like this. You have a graph G. Is that okay? A very big graph. And then you start from any vertex. You start from any vertex. So you walk to a new vertex, and each time you pick an edge that you have not used before. So you pick an edge, you pick an edge, you pick an edge, you pick an edge, whatever. And at some point, you must go back to this vertex. It is because of what? Because the number of edges is limited. And then every vertex has even degree. Okay, at the beginning. So that this is the only vertex. So once you have this vertex as the starting point, it is the only vertex that has an odd degree of edge that we have not used. So when this vertex moves to this one, we immediately use a new one. So this vertex has an even degree resumed. So as we continue this process, all the vertices that has in the graph must have even degree. And then if it has even degree, what does it mean? It means that whenever we enter, we must be able to leave. So the only time that we can stop must be we are stopping at this vertex. Is that okay? So let me give you an example. Okay. So let's start with this one. Let's start with this one. Let's say this is A. Is that okay? Now using my process, I go to A and visit a new vertex. Let's call B to this one. Is that okay? Then I may be choosing this one. Let's call it C. Is that okay? A to B to C. And then from C, I may be choosing this one as the next one. Let's call it D. D may be choosing this one as E. E may be choosing this one. And then this one now, it enters, it must have at least one vertex, one edge that we can leave. So we can get back to this one. So now we can get back to here using this process. If you understand what I'm talking about, could you please raise your hand? Okay, good. Is that okay? Good. So using this process, we must end, because each time we use one edge. And whenever we end, we must go back to the starting vertex that we picked. Okay, because if it is not the starting vertex, there must have an edge that leaves. Enter, leave, enter, leave, enter, leave, enter, leave. And then we have to stop when we cannot leave. And then this is the only case. Is that okay? Now, once we have this one, we can remove this cycle. So this is a cycle. This is a circuit. So we have a circuit here. And then so if you remove this, then what will happen? We will be left with a graph such that such that the degree of each vertex is even. Because we are removing this, we are removing even number of edges from each vertex. So we have this one. Okay, it may be more. Okay, so this is in this case. So let's say this case. In this case, what does it mean? In this case, because the original graph is connected, so we have a cycle here, and then it is connected to some graph. Connected to some graph. Let's say it is a small graph. Let's say G prime, such that every degree of a vertex is even. So in that case, by induction, we can have an Euler circuit here. So if I have an Euler circuit here, then what does it mean? It means that there is an Euler circuit here. So if an Euler circuit here and Euler circuit here, then we can start visiting from here and then go here and then come back and then do this. Is that okay? Now this is an example, but this is not the only case. In the general case, it looks like this. So let's say we have a graph of. So let's say this is A. So maybe we are choosing B and then C and then go back to A. So we can choose something like this. So if we choose something like this, then this is the Euler's, this is the cycle that we can generate from a process. But then it is attached to some graph G1 and attached to some graph G2 and attached to some graph G3 and so on, such that each of them is a graph with even degrees of all the vertices. So by induction, this is a small graph, this is a small graph, this is a small graph. So we can compute the Euler circuit of this one, compute the Euler circuit of this one, and join them together. So originally we are moving A, B, C back. So what should we do? We move to A, B, because there is a joining here. We visit the Euler circuit here of this part. Come back to B, move to C, visit the Euler circuit here, come back to C again, and then move back to A. Is that okay? And in that sense, whenever the graph has even degree at all the vertices, then it must have an Euler circuit. If you're okay with this, could you please raise your hand? Okay, good. So finally, so this can be checked by a computer program easily in linear time. So finally, how about Euler path? We have not talked about Euler path. So the difference between Euler path and Euler circuit is that Euler path does not require the starting point to be the same as the ending point. Okay? But you can see that if a graph has an Euler path, and if the starting and ending are the same, then that means that it has an Euler circuit. If the starting and ending are not the same, then what does it mean? That means that if we join them together by an edge, then this will become an Euler circuit. Is that okay? So a graph has Euler path is either two cases. Either it has an Euler circuit at the beginning, or we can add an edge so that the graph has Euler circuit. There are just these two cases. Okay. So for the first case, check if it has an Euler circuit. For the second case, check if we can add an edge so that it has an Euler circuit. So how do we know which edge to add? It is easy. Because if we add the edge and then it has Euler circuit, then this must have odd degree at the beginning without counting this edge, and this has also odd degree at the beginning without counting this edge. Am I correct? Because when we add this one, it becomes even. So we can immediately improve that. A graph has, so we can really write it down. So G has an Euler path if and only if the first one is G is connected, and the second one is G has at most two vertices with odd degree. And that's it. Okay, either G has 0 vertices of odd degree, which means that it has an Euler circuit, or it has two vertices of odd degree. In that case, we can join an edge between the two odd degree vertices and then make an Euler circuit. Okay, and how about I'm writing at most two vertices? So at most two means that 0, 1, or 2, right? So can a graph has one vertex with odd degree? Can it? Okay, I have a graph. Can a graph G has exactly one vertex with odd degree? Is it possible? Yes or no? So a graph can have two vertices or 0 vertices of odd degree. Okay, this is what I want to write, but I'm writing at most. So I'm actually saying that you can't have a graph with exactly one vertex of odd degree because the total degree is even. By handshaking lemma, I hope you still remember, the total degree, the summation of degree of all the vertices is an even number. So you can't have exactly one odd while all the others are even, because the total sum will be odd, and it is impossible. Okay, that's it. So sorry for overrunning the class, and sorry about the mistakes. Okay, so this is the mistakes. I hope you won't be confused a lot. Okay, that's all, and let's continue the discussion on Wednesday. Okay.